welcome to lesson 3-5 residual plots and mathematical models. And we are still on problem set number 1 for this lesson. And in the previous lectures or in the previous videos, we answered part A of this problem. So again, just to recap the entire problem set for this lesson 3-5, problem set number 1. This is about a radius-on air pressure problem. So we're still on residual plots and mathematical models. So meteorologists release weather balloons, such as the one you see here, called radius-ons each day to measure data about the atmosphere at various altitudes. So this is the figure 8-4F. And this table show altitude in meters. So I think we have discussed about that. And for letter A, we have actually graphed and found the regression of this data. So we are now on letter B. So for letter B, put another list in your grapher for the residual of each point. Then make a residual plot and sketch the result. Do the residuals follow a definite pattern or are they randomly scattered? What real-world phenomenon could account for these deviations? Okay, so it's just a review. Residuals mean that we are going to subtract your y hat from the y. So for every y here, this is our y. Is it our y? Wait. Yes, our y is pressure in millibars and our height is meters. So this is our y and this is our x. Am I correct? And as a recap, this is our y hat. Then this is found using the regression function in your graphing calculator. So we got this y hat here, and all you need to do is to create a table for your pressure for the y, and then your y minus y hat. So for every x here, you would get a definite y hat value, and your x is in terms of height. Okay, so how many data will you get for your y minus y hat? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 data. Okay, so anyway, I don't want to make this a little bit long for the explanation because we have done it in the previous videos, and I have already explained to you how to get the y minus y hat in the preceding lectures. So without further ado, I am just going to give to you the oops, that's the wrong program. So we have this is the graph of the residual. Okay, and you can find this graph by getting all the inputs for your y minus y hat, which, as I have said, you have to get the value of your y hat for every x here, and then substitute it from your y value for every x also. Okay, so you could actually check that. Get your grapher and then try to graph this using your graphing calculator and the inputs. So what do you think about this pattern? Now they have it has or the residuals have a very definite pattern. As you can see, it goes up, and then after this curve, if you are going or if we are going to trace the plots, okay, then we would definitely have a curve here which increases upward, and then it suddenly stops here, and then it goes downward again, and then in this pattern this is likely to increase again. Okay, but we are already done from that, from 400 to 18195 for your x. Okay, so they have a very definite pattern. Now, any phenomenon that you know uh, that would have this kind of graph would certainly fit the residual plot. Okay, so it varies. So you could actually make some research about it also, and just think of a phenomenon or any event that increases and then suddenly shifts the curvature and then decreases sharply again and then somehow settles in here. So it's somehow it is flexible. Okay, so this kind of pattern is flexible. Okay, so that's it for letter B. So letter C, based on your residual plot in part B, could the exponential function be used to make predictions of pressure correct to the nearest millibar if this accuracy were necessary? So what do we need to get here? Okay, now what we have to get here is actually the mean of the absolute residuals. Okay, and what is the mean uh, of the absolute residuals? Okay, now in this case we have to really get the y minus y hat and then compare it with the absolute mean of the residuals. Okay, so let us do that. It will just take some time, but it's okay, and it's better than to not understand it really well. Okay, so let us compute for all the y hats here. But it would be easier if you have the grapher or the graphing calculator for you to have an easy computation of your y hat. So now our y hat is this thing here, okay? And this is our y. Okay, so what is our y hat? First, we determine our y hat. Y hat is 1076.9102 times 0.9998 raised to x, and these are our x's. So if our x is 400, first let us define our function, and our function is 1076.9102 times 0.9998 raised to x, and our x is 400. So in this case our x is, okay, let me have another color. I want this color, so it's 994.105. So I am going to approximate it to the nearest thousands. Okay, what about my y for x is equal to 620? Okay, oops, what happened? Okay, replay. Well, I'm solving with my scientific calculator. It will take quite a while. Okay, so we have 620, and this will give me 951.308.30. Let's say 309. Okay, just rounding this off. And then my x is 800. So this would be 917.668. And when my x is 1220, that's 843.725. Okay, now let me use another color for a pen just to segregate every force. Okay, so what if my x is 1611 or 1611, yes. So this will give me 780.254, and when my x is 2018, 2018. You know, statistics is a little bit, what do you call this? It's a little bit of working hard and working patiently because we have to get all the data. Okay, so 719.251. Okay, and if my x is 25, so 2500, I will have 653.146. If my x is 3009, so 3009, then I will have 589.922. Okay, if my x is 4051, then my y hat is 400. Okay, let me use another color this time. So I want to use green. So this is 478.938. If my x is 5000, that's 5000, then I have 396.134. If my x is 6048, 6048, then my y is 321.221. If my x is 7052, so 7052, then I have 262.778. Okay, next I would like to use brown, and my x now is 8075. 075. This will be 214.153. Okay, what if my x is 9005? 9005 involves a lot of tasks. That's 177.802. If my x is 10,042, 10,042. Okay. Note that we are actually modeling this data on an exponential function. Okay. So 10,042 will give me 144.496. If my x is 11086, 11086, I will have 117. So it goes down, huh? 0.264. Now I want blue. If my x is 12,151, 12,151, that would give me 94.766, assuming that I have a correct y hat. Yes, I do have. Okay, so what if my x is 13024? 13024. So I would have 79.582, right? If I have 13024, not 14004, 2004, I would have 65.416. And if I have 15134, 15134, that will give me 52.1826. And going back to red, we have 1617 for x, 16197. That would give me 42.188. Then if my x is 17120, 17120, then I would have 35.076. And if my, I call this, x is 18195, 18195. So I will have 28.289. Okay, now let's go to y minus y hat. So y minus y hat. So 965 for the first row, 965 minus 994.105. That's 29, negative 29 point, negative 29 point. Okay, I don't like red now. I want this one. Negative 29.105. 940 minus 951. 940 minus 951. So that would give me 0.309. 0.309. That's negative 11.309. Okay, what about 920 minus 917? 920 minus 917. 0.668. So this is 2.332. It's positive. Okay, we have 875 minus 875 minus 843.725 equals 31.275. Okay, what else? We have the next, let's say, the next one will be 835 minus 780. 835 minus 780.254. So that will give me 54.746. And then I have 795 minus 719, 795 minus 719.251 will give me 75.749. So this will continue up to here, up to the last. Okay, and we have y minus y hat, so and so on and so forth. So if we are to get the residuals here, y minus y hat, using our original pressures, then we could see that this level you can see here, right? That's the plot of the residual. So the residual could actually go until negative 52.7 millibars, while the mean absolute residual, if you take the mean absolute residual, okay, so y minus y hat, the mean of that is equal to 16.9 millibars. Okay, so the mean is 16.9 millibars, but the residuals go as far as negative 52.7 millibars. So what is being implied here? What is being implied for letter C? For letter C, you cannot make predictions of pressure correct to the nearest millibar. Okay, because your functions, I mean your y hat function, okay, the residual takes somewhat of there is discrepancy in the residuals. Okay, so the answer here is no. Okay, the exponential function cannot be used to make predictions of pressure correct to the nearest millibar because, as I have said, the residuals are as great as negative 52.7 millibars, while the mean absolute residual is 16.9 millibars, which is, the discrepancy between the mean absolute millibar and some of the residuals are too great. Okay, so the exponential function cannot be used to make predictions of pressure correct to the nearest millibar. Okay.